Exploring time travel, a journey through space and gravity. Imagine space as a vast, endless fabric, something like a trampoline net that stretches and bends with every massive object that moves across it. Now, picture this trampoline being twisted into the shape of a pretzel, and suddenly, you could be traveling backwards through time. Sounds like science fiction, right? But this is exactly what some of the greatest minds in physics have been exploring for centuries. The idea of time travel isn't just a concept from movies or books. Theoretical physicists have been working for decades to understand if and how time could bend and allow us to journey back to the past, just like we travel through space. Let's begin by taking a step back and thinking about how humanity first made giant leaps in space. In 1969, we managed to send astronauts from Earth to the Moon, a journey spanning 250,000 miles, and then back again. But how did we manage this incredible feat? The answer lies in gravity. But not just any gravity, Newton's understanding of gravity. Sir Isaac Newton's work in the 17th century laid the groundwork for how we understand forces today. However, what Newton didn't fully grasp were some of the deeper mysteries of space-time. Enter Albert Einstein. One of the greatest minds to ever walk the earth, Einstein radically changed our understanding of gravity. While Newton had described gravity as a force that pulls objects toward each other, Einstein revolutionized this idea with his theory of general relativity. In fact, Einstein famously called gravity a deception. This doesn't mean that gravity doesn't exist. Rather, Einstein's theory suggested that gravity isn't a force at all, but instead a result of the way massive objects bend and warp space and time itself. Einstein's breakthrough showed us that the fabric of space and time isn't a flat, static thing. Instead, it can stretch, curve, and twist, much like a sheet or fabric. Picture it like a trampoline again. If you place a heavy object, like a bowling ball, on the fabric, it creates a dip. Now, if you roll a marble across the trampoline, the marble will be drawn into the dip. This is essentially how gravity works. Larger objects, like the Earth or the Sun, warp spacetime so much that it pulls smaller objects, like the Moon or Earth's satellites, into orbit around them. But wait, there's more to this story. Einstein didn't just reveal how gravity works, he also introduced time dilation, one of the most mind-bending ideas in physics. According to Einstein's theory of special relativity, time is not a fixed constant. Time can actually slow down depending on how fast an object is moving or how much gravity it's experiencing. Imagine you're in a spaceship traveling at nearly the speed of light. From your perspective, time would pass more slowly than it would for someone on Earth. This concept might sound strange, but it's been confirmed by experiments, including one where atomic clocks aboard airplanes showed that time does, in fact, run slower the faster you travel. This brings us to the fascinating idea of time travel. Time dilation, as strange as it may seem, could theoretically open the door to time travel. For instance, if you could travel near the speed of light, you might be able to jump forward in time without experiencing it as we do on Earth. While this has been tested on a very small scale, with astronauts experiencing time dilation while in space, we're still far from being able to travel through time the way we imagine in science fiction. But time travel isn't just about speed. It's also about gravity. Let's dive into how Einstein's theories affect our understanding of time when it comes to massive objects like black holes. Imagine a black hole, that mysterious cosmic object where the force of gravity is so intense that not even light can escape it. Black holes are the ultimate example of space-time being warped and twisted. When you get close to a black hole, time itself is stretched out. Near the event horizon, the point beyond which nothing can escape, the effects of time dilation become extreme. To an observer far from the black hole, time near the event horizon would appear to almost freeze for anything trying to escape. Now, back to time travel. If we could survive the incredible forces near a black hole, theoretically, we could experience time in a completely different way. For someone far away, years might pass in the blink of an eye, while someone near the black hole could experience only a few moments. While this kind of time travel sounds like science fiction, it's grounded in real science. We know time dilation happens. We just haven't yet figured out how to safely harness it for time travel. In fact, physicists have been studying these time-bending ideas for decades. In 1992, Stephen Hawking proposed a fascinating hypothesis known as the chronology protection conjecture. According to this theory, the laws of physics prevent time loops, or closed time-like curves, from forming. This means that time travel to the past, where you could go back in time and alter events, might be impossible. Hawking argued that the universe has built-in safeguards, cosmic protections, if you will, that prevent these paradoxes. His hypothesis suggests that even though time travel might be theoretically possible, the universe's laws of physics will prevent you from actually doing it, ensuring causality is maintained. So, what does this mean for us? Does it mean that time travel will forever be just a concept for the movies? Not necessarily. While the idea of traveling backward in time raises paradoxes, like the famous grandfather paradox, where you could theoretically prevent your own existence, the exploration of time remains one of the most exciting frontiers in science. With ongoing advancements in quantum mechanics, general relativity, and cosmology, who knows what the future holds? In fact, contemporary physicists are working hard to expand our understanding of time and space. The discovery of gravitational waves, for example, was a major breakthrough in 2015. These ripples in spacetime, caused by massive objects like black holes colliding, help us better understand how spacetime behaves under extreme conditions. This has opened up new possibilities for studying time dilation and the nature of time itself. We're also learning more about black holes and the event horizon, the boundary around a black hole. Beyond the event horizon, the very fabric of spacetime breaks down, and traditional physics can no longer describe what happens. Time and space lose their usual properties in this extreme environment, making it a perfect testing ground for the limits of our understanding of time. One real-world application of Einstein's theories is the GPS system. These satellites orbit Earth, where the effects of gravity are different than on the ground. Without accounting for time dilation, GPS systems would be wildly inaccurate. The fact that we can navigate with pinpoint accuracy today is a direct result of understanding how time behaves differently depending on gravity and velocity. As science continues to evolve, so does our understanding of time. Are we still far from mastering time travel? Perhaps. But we've only begun to scratch the surface of understanding the true nature of time, gravity, and the universe. Whether time travel becomes a reality or remains a fascinating theoretical idea, the journey to uncover its secrets is just beginning. So, what do you think? Is time travel a real possibility, or is it just an impossible dream? Let us know in the comments below. The quest to understand time continues, and perhaps one day, we'll have the answers. Thank you for watching, and we'll see you soon with another